Hi, I'm David Gesswein. I showed operation of the original PDP-8 model for VCF West running the basic paper tape system. I'm going to show you a nicely configured 8i with several peripherals for this video. This configuration is much nicer to use. It can assemble a previous demo in 9 seconds and this demo in 30 seconds. The 8i is the first PDP-8 using integrated circuits. This 8i has 8K of memory, the extended arithmetic element multiply divide option, the high-speed paper tape punch and reader, and a plotter interface. The plotter you can't currently see. The PDP-8i was introduced in 1968. Attached to the PDP-8 is a DF32 32K word disk drive, which I'm actually going to use this time, and AX08 laboratory peripheral. And I'm using a VT52 terminal instead of the teletype. The VT52 is from 1975. The DF32 is a fixed head disk with 5 4-pole heads, giving it 20 tracks, with 16 used for data. Since the heads land on the disk surface, DEC recommended not powering off the drive. I have had it working, but it was not terribly reliable. I'm using a board that emulates 4 DS32 expander disks and stores the data in battery-backed SRAM on a board I made. That gives me 128K words of storage. This drive is not divided into sectors and can read and write down to a single word. The AX08 is a multi-channel ADD converter. There are 4 inputs on the front, and I'm using one of them. It also has digital inputs and outputs, crystal clock, RC clock, which I'm using as a sample clock, and a point plot display generator, which I'm using to drive this RM503 oscilloscope. What I'm going to demonstrate is capturing a signal with the AX08 and displaying it on the point plot, doing an FFT and displaying the spectrum, then plotting the signal and spectrum on the plotter. PDP-8s were frequently used in laboratories and industrial control where they would be doing similar things. The FFT I'm using is DECA's 8143 from 1968. DECA's was a digital equipment users group, which people could submit programs to that DECA's would distribute for a nominal cost. The write-up has an undated change to improve the rounding, and one from 1973 submitted by a person at Turkish University Electrical Engineering Department that corrected an error in data scaling that could cause overflow and incorrect results. My plotter is a Calcomp 563, which we'll see later, probably made in 1973. This manual was from 1969, so the model dates back at least that far. All the smarts for the plotter are the software running on the PDP-8. The instructions are just generating X, Y, or both step pulses, which the plotter uses to drive the stepper motors. Each step is 0.005 inches, and you can plot it up to about 1.5 inches per second. Later pen plotters were intelligent and much faster, with the HP model I checked capable of doing 32 inches per second. Pen plotters have been superseded by inkjet plotters. When you're plotting data, grid paper like this was available that allowed you to then accurately measure the points on your plots. And here's some of the accessories, where you have these optical sights that you'd use to align to the grid. And there was also an adjustment wheel on the plotter you would use to match its motions to the exact grid on the paper, since paper size changes slightly. There were a number of options. This is a pressurized ink ballpoint. It's basically a smaller version of the Fisher Space Pen that was available in a number of colors. They had normal ballpoints. And we had the liquid ink pen with the liquid ink. and felt tip pen. And the various pen bodies that they would go into. I'm now going to start the PDP-8i. I'm running disk monitor system. I'm just going to restart the operating system that's still in the non-volatile core memory. Starting address is 7600. Load address. And start it running. I'm now going to load my program. I'm going to load it in multiple parts. The first part is the FFT routine itself, then a patch file for it, and then my program. Now tell it the starting address of my program, which is 200. And tell it to start executing. Control P. Now you can see on the oscilloscope the sine wave that I'm putting in from this function generator. Each data sample is one of the dots drawn by the point plot. Now if we crank the frequency up, it gets a little harder to tell it's a sine wave. We'll freeze that. And then take the FFT. And you can see here the primary frequency of the sine wave. And the rest of it is no significant energy. Started capturing again. And we'll crank up the amplitude. So now it's significantly clipped. Freeze it. FFT. And now you can see the primary frequency and the harmonics that have come up from the clipping. And it tells me that I'm sampling at almost 20 kilohertz.